Welcome everyone, we've made it. Here is the Finite Math Final Exam Review, which is hopefully highly anticipated. And I'm going to go a little quickly because of course we have a lot to discuss, so let's just jump right into things. And for one, I'm asked to find the x and y intercepts. So for A, well, how do you find x-intercepts? You set y equal to 0 and solve for x. So we get 0 is equal to negative 3/4 x minus 9. We can add 9 to the other side to get negative 3/4 x. We can get x by itself and multiply on both sides by the reciprocal of negative 3/4, which is negative 4/3, just like that. And of course we have cancellation. Double negative is positive, 3's cancel, 4's cancel. That's the whole point of multiplying by the reciprocal. And here actually there's cancellation too. 3 goes into 9 3 times. So we have in total is that x is equal to negative 12. So I'm going to write the point negative 12 comma 0 as our x-intercept. Y-intercept super easy in this case because y is already by itself. So when we set x equal to 0, what do we get? We get y is equal to negative 3/4 times 0 minus 9. Anything times 0 is 0. So this whole thing zeroes out and we just get y is equal to negative 9, which tells me that the y-intercept is then the 0 comma negative 9. Good. Now on to B, same exact idea. To find x-intercepts, we set, well, y equal to 0 and solve for x. Now in this case it's a little different because what we end up getting is, let me write it over here, 0 equals x squared minus 7x plus 6, which is of course a quadratic equation in x. So to solve for x in this case we want a factor. You could also use quadratic formula, but I'm going to handle this one in particular by factoring. So I'm looking for two numbers that will multiply to the last one and will add to the middle one. And this of course works because there's no number in front of x squared. Otherwise, as we'll see in later problems in this review, there's different techniques you would use to basically undo foiling. But the numbers in this case are, well, let's see, I guess negative 6 and negative 1 do the trick. They multiply to positive 6 and they add to negative 7. So with that being said, this left-hand side, or right-hand side I should say, sorry, factors as x minus 6 and x minus 1. So then by the zero product property, we get x is equal to positive 6 or positive 1. So our x-intercepts are then 6 comma 0 and 1 comma 0. And again, much like for part A, y-intercept is a cinch, because for y-intercepts, when you set x equal to 0, the fact that, well, y is already by itself in our equation, we get y is equal to 0 squared minus 7 times 0 plus 6. And of course, these all zero out, because they're multiples of zeros basically. We get y is equal to 6, which as a point is a point 0 comma 6 because its x value is 0. Good. So that was number 1. Now let's look at number 2. So now for number 2, we're asked to solve for x, and of course we have different types of things going on here. Here we have a linear equation, quadratic equation, and this is exponential. So let's take a look. For the linear, I'm going to notice there are fractions involved. So if you want to get rid of fractions right away, we can certainly do so by multiplying everything by basically the least common denominator, which in this case is the least common multiple of 2 and 3, which is just their multiple, their product, 6. So if you multiply everything by 6, here's what we get. 6 times 5x is going to be 30x. 6 times 1/2, so this 6 hits each of these parts of the equation. So we did the first part. 6 times 1/2 is 3, so that takes care of this whole part. So then we can just distribute that 3 in. 1/3 of 6 is 2, that takes care of that whole part. Now we can distribute here and here, I guess. And we get, let's see, 21 plus 18x equals 18x plus 4. And there's actually a few kind of coincidental things that happens here. Notice you can just subtract 18x and they cancel out. And similarly, you can actually subtract 21 to this side. And right away, we get 30x by itself. So let me write the result over here. We get 30x is equal to, well, 4 minus 21 is negative 17. And then finally dividing by 30 gives us our answer. X is equal to negative 17 over 30. Perfect. Another way of doing this is embracing the fractions, and it's not too bad. But yeah, instead you can get rid of fractions altogether in any equation actually. Here, let's see. So I'm going to Well, I'm just going to simplify as much as I can. So I'm going to distribute this 3x. So we'll get 3x squared plus 6x, of course. And now I can see, like I was saying earlier before starting this problem, I said this was quadratic because I noticed x times x was x squared. Now to make it in our standard quadratic form, we're going to move everything on one side so there's zeros on the other. So specifically, I'm going to subtract 13x and 6 to the left side. So let me just kind of squeeze it in here. So here they cancel out and we get 0. And here, these two combine to negative 7x, and let me just write that in between. And let me actually write the result over here. So we get 3x squared, there we go, minus 7x minus 6 equals 0. And if you can't handle the factoring here, you can certainly use quadratic formula. In fact, it's very possible the quadratic that you're given is not even factorable. So in that case, well, you would have no choice but to use quadratic formula. But in this case, it actually does factor. Let me kind of try to reason out what it factors as. So I know it has to look something like this if it is indeed factorable, because 3x times x is really our only option to get 3x squared. Now 6, to get 6, there's a few options. Either we have 1 and 6, 2 and 3, or the other way around, because since this 3x is here and this x is here, they may be different. So really there's a total of 4 different combinations, so we can guess and check. And I'm going to try to do that and try to play with the middle term here. So let's take a look. What if it is 6 and 1? So if it's 6 and 1, then this inner term is 6x, and this outer term is 3x. But notice there's no way to change the signs of 3x and 6x to combine to get negative 7x. So that combination is not going to work, so now let's try 1 and 6. And 1 and 6 you'll see is actually even worse. Because if you change their signs around and add those two middle terms together, either you'll get 17x or negative 17x, or 19x or negative 19x, which is not negative 7. So that means 1 and 6 is out for the count, and it has to be 2 and 3 in some order. So let's just pick at random this one. Maybe we get lucky. And I think we did. Because here we get 2x for the inner term. For the outer term, we'll get 9x. And we can change the signs to actually get negative 7 as a result. This would have to be negative, and this would have to be positive. Perfect. So that means if we want positive 2x, this sign has to be positive, and that sign has to be negative. So when I'm writing those negatives, they're just they're placeholders, really. I'm not saying that it has to be negative. I'm just writing negatives because they're easier to change to pluses. So that's just my way of doing it. And I have shown other methods of factoring in this class, but I just wanted to showcase this one in this problem. So now that we have that, you can check by foiling this out to see that you indeed get this thing on top. So it works out. And now finally, by the zero product property, we get 3x plus 2 is equal to 0. Subtract 2 divided by 3. You get x is equal to negative 2/3. Or x minus 3 is equal to 0. Add 3 to the other side, you get x is equal to positive 3. So these are the only two solutions there. So here's one solution. Here there was two. Now let's take a look at this one finally. Now for exponential equations, you always want to try your best to write each side of the equation in the same base. So think of like a common base. So notice here on the left, this is 2 to the 3x plus 2, and 2 can't be factored. So I'm just going to leave this side as that, actually. 8, we can write as a power of 2. In fact, the fact that we can factor this 2 implies that we can write each of these as powers of 2. And it's true. Because if you look at 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, and 2 to the 5, let's say, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8, 2 to the 4 is 16, and 2 to the 5 is 32. So notice in this list, we're just multiplying the previous one in the list by 2 to get the one we're at. Right. So with that being said, 8 is 2 to the 3rd. 32 is 2 to the 5th. So in actuality, if we recall exponent properties, we can multiply these ones and then add that to this exponent. So altogether, this is 2 to the 15x times 2 to the 5th, but since they have the same power, or the same base, I should say, we can add the powers. So 15x plus 5. So this is the same as this for that side. Now on the left, Now that we have a common base, now we can use, I forget what we called it in this class, but normally it's referred to as the one-to-one property of exponents. And basically what it says is that if your bases are the same on each side of an equation, then the exponents must be the same as well. If your bases, of course, are bigger than 1 and non-negative. And this is certainly true here. So we end up getting, using this one-to-one property, is the exponent on the left is equal to the exponent on the right. And now really what we have at our hands is just, well, a linear equation, which we can solve kind of like how we solved 2a. So let me just move the x's to the right, I guess, and the non-x's to the left. So these cancel, we get 12x is equal to -3 divided by 12. And we get x is equal to -3 over 12, of course, reduces to -1/4. And that is our answer for 2c. We finished 2, and now let's move on to number 3. Right, so now for number 3, it's asking us to solve for x much like number 2, only we have to approximate the 3 decimal places when necessary. First, I want to recall a few things. I only really want to recall 2 things, even though actually I could say more here because we saw a ton of logarithmic properties when we discussed logarithms. But the biggest ones were these. The definition of logarithms, log base b of y equals x, is the same thing. It's equivalent to the so-called exponential form, b to the x is equal to y. So these 3 things, b, x, and y, just move around in this way. This last one here is called the change of base formula, which basically says that the log base b of x can be either written as ln of x over ln of b, or log of x over log of b, where ln is log base e, and log without the base is a log base 10. Now in reality, we can change the base to anything. So in reality, I could say log base b of x is the same as log base c of x over log base c of b, where c is any number, any positive number, bigger than 1. But anyways, I digress a little bit. Let's move on. So here I'm going to convert this to its exponential form. So notice the base is 2. The exponent actually is what the log solves for. So notice x in this general case. So it's going to be 2 to the 8 is equal to x. So that means our answer is just whatever 2 to the 8 is. And I guess we can use our calculators here. I don't want to think about it too much, but we saw that the 2 to the 5th was 32. So this is that times 8. So we kind of have to multiply by 2 a few more times if you were to do this by hand. So you get like 32 times 2, which is 64, times another 2, which is 128, and times one last 2, which is 256. So this is just 256. But again, you can use your calculator there. So that wasn't too bad, but it gets, just convert it to exponential and then solve for x from there. In this case, can we just convert to logarithmic? We can. Let's do that. So here, log base, what's the base? This is log base b, and this is b to the x. This is 5 to this, so the base is 5, of what the exponential is equal to, y, in this case is 4, is equal to the exponent of b, which in this case, the exponent of 5, is x plus 1. So all really we have to do to get x by itself is subtract 1. So we'll get that x is equal to -1 plus log base 5 of 4. And this is exact, but it says to approximate to 3 decimal places when necessary. So you could take this as being your final answer, but it's exact. If you want to approximate this to 3 decimal places, you can use your calculator and the fact that log base 5 of 4 is ln 4 over ln 5. And then let me see what my calculator gives me. It, of course, gave me -0.139 after rounding to 3 decimal places. And recall here how I got ln of 4 over ln of 5, which is basically using the change of base formula, as I mentioned previously. Good. So now this one is actually a little more straightforward than b, believe it or not. So we're going to do the same thing, convert this to logarithmic because it's an exponential form. So I'm going to say log base, the base is e, of what the exponential is equal to, 20, is equal to 2x minus 1. Notice that this is just ln of 20. And then all we need to do to get x by itself is add 1 and then divide by 2. Add 1 to the other side like this. Those cancel. And then divide both sides by 2. we get this for our final answer. So let me just write x is equal to 1 plus ln 20 over 2 as an exact answer. But if we approximate, well, let's see what the calculator gives us again. And after rounding to 3 decimal places, I got 1.998 as an approximation to 3 decimal places of accuracy. Now, something I must say here is that when you're using your calculator in this way, if you got something different, you may not have written it the correct way in your calculator. So for me, I'm using a TI-83 Plus, which I'm assuming everyone in my class basically is using something like that. You have to put the numerator in its own set of parentheses, or else you may get something a little different. Okay, so with that being said, let's move on to number 4 now. Right, so for this problem, it's a problem involving finance, and it says how many years will it take $10,250 to grow to $25,000 if it is invested at 1.5% compounded, A monthly, B biweekly. So let's recall the compound interest formula is A is equal to P times the quantity 1 plus R over N to the NT, where P is the initial principal, A is the amount after a certain amount of years pass, R is the rate, the yearly percentage rate, N is the amount of times compounded per year. So basically it's this wording, we have to translate that into a number as far as how many times per year. And then T is the amount of years. So now there's a few things we get for A. So right away, monthly tells me N is 12 because monthly means 12 times per year. So monthly says months, and there's 12 months in a year. So that's basically what I'm thinking. T is unknown because we want to find how long it'll take. R is given, but I need it in decimal, so that's going to be 0.015. Good. P is the initial amount, that's 10,500. And A is the final amount, which is 25,000. Great. So now what we need to do is plug these into this formula and solve for T. Let's see if we can do that. So we get 10,500 equals, I'm sorry, did the other way around, didn't I? There we go. 25,000, 10,500 equal, there we go. Parentheses 1 plus 0.015 over 12 to the 12t. Now I'm going to use my calculator a bit to try to tweak this equation. I don't want to approximate too much, but I am going to approximate the inside. But again, the more you approximate, the more your answer will actually deviate from the actual answer. So I'm not going to approximate very much. In fact, I encourage you to use the answer key function in your calculator to keep everything within the calculator to avoid errors, basically. But the first thing I'm going to do before we jump to that is I'm going to divide both sides by 10,500 because there's a few cancellations here, these two zeros namely, and then I guess we can divide by 5 as well to reduce this. I'll use my calculator for that as well. So using my calculator, let's see if we can translate this into a more palatable equation. So let's take a look at that. All right, not too bad. So as it turns out, this 250 over 105 actually just reduces by dividing by 5 to 50 over 21. This, as it turns out, is not really a continuous fraction. It stops at some point. So this part is just 0.00125, making the whole base 1.00125. Perfect. So now we're in a good spot to solve. This is an exponential form to solve for t in the exponent. We want to convert this to logarithmic form. So we'll have log base 1.00125 of 50 over 21 equals 12t. But let me write that part over there, the 12t part over there. Good. And now, of course, to get t by itself, we'll just divide both sides by 12. So I hope you don't mind me doing this. I'm just going to say t is equal to 1/12 of this logarithm. And to compute this into my calculator, I'm going to use, well, what we saw with number 3, which is the change of base formula. I'm going to use the ln version of that. So this is going to be 1 over 12 times ln of 50 over 21 over ln of 1.00125. And we may need to be a little careful how we plug this into our calculator. We may need parentheses and whatnot. But I'm going to do that right now, and let's see if you get the same thing I get. So I actually rounded to 1 decimal place, and I got 57.9, and that's in years. Now, if we're compounding more often, then the yearly interest is being applied more often, so we expect to wait less time to meet this goal. So we're going to run through the same argument here, only instead of with biweekly. Now everything changes. Well, everything stays the same except for one thing changes, is what I really meant to say. So what changes? Well, n will change because instead of compounding it monthly, we're compounding it biweekly. So here in this case, n is equal to, well, there's 52 weeks in a year, so biweekly is every other week, so that means a total of 26 times per year. Half of 52. Perfect. So now I'm going to run the same argument here. In fact, the only real thing that'll change is this denominator and this coefficient of t in the exponent. So when we divide by this, we'll still get 50 over 21. So we'll get 50 over 21 equals 1 plus 0.015 over 26 now, and then to the 26t. Now I'm going to clean this part up in my calculator, but from there it's going to be the exact same thing. In fact, I think you can kind of tell really what this is going to end up as if you kind of compare and contrast. This will be t equals 1 over 26 log base whatever this amounts to, so I'll kind of leave my calculator for that, and then of 50 over 21. Good. And then we can use, well, the change of base formula, so we get 1 over 26 times ln of 50 over 21, good, over ln of whatever this base is, again, just by using a calculator. We may need to round, but if we just kind of keep it stored in our calculator, we'll avoid any accuracy errors. And then from there, we can round to see how many years. So now I'm going to use my calculator to fill in all the blanks, and let's see what we get. So you have to be, again, a little careful, because these, of course, are the numbers I got. Now, if you round, this will round to, the base will round to 1.00058. But if you actually use that number as is, you will get about 57.5, not 57.9. So the reason why I got 57.9 is because I'm not really using 1.00058, even though I'm writing it. I'm using the whole thing my calculator gives me without actually rounding. So that ensures I'm more accurate. Okay, that's the first thing. The second thing is that, what did I say earlier? I said since we're compounding more often, you'd expect it to be less time, but it seems to be the same amount of time. It's 57.9 years. And that's, of course, just because we're rounding. In fact, in reality, this rounded from 57.86, this rounded from 57.85, and well, the difference there actually amounts to just about a week, believe it or not. So this will still be last time, not by much though. Anyways, that concludes number 4, and now let's move on to number 5. Okay, so number 5, much like number 4, is a problem in finance. The only thing is it's a little different. So instead of finding how long it'll take, it's actually a little more straightforward. It asks how much will be in the account after a certain amount of time has passed. So it says if $18,000 is invested at 3.25% yearly interest rate, but compounded continuously, so the formula is a little different, and I recall that here, but that we'll get to that in a minute. What is the amount after 3 years? So again, I recall this formula. This is the continuous compound interest formula, and A, P, R, and T are the same as they were in the compound interest formula. A is the amount after t years, P is the principal, R is the yearly interest rate, and T is the amount of years, of course. But E, well, we know what E is. It's 2.71828. It's in our calculator. We don't have to remember it. But yeah, really all we're doing is plugging in these numbers here into this equation. But we have to figure out what's what. So this is our initial amount. So that's going to be P, because that's the amount we're investing. We're starting off with that amount. Okay. The next thing we need is, I guess, R. R is the rate in decimal. That's going to be 0.0325. Good, because you move the decimal to the left twice. And T is going to be 3, because, well, 3 years. Good. And A is unknown. So all we need to do really is just solve by plugging this in. So we'll get A is equal to 18,000 e to the 0.0325 times 3. Now all you really have to do is just plug this into your calculator. E to the is second ln on the calculator, and what my calculator gave me was $19,843.41 if you round to the nearest cent. Okay, good. So that was pretty simple, pretty straightforward, just a use of this formula that we've seen quite a bit in when we discuss finances anyways. So now we're going to move on to number 6. All right, so here for number 6, we're being asked to solve these systems of equations, but by any method. So we can use elimination, substitution, method of matrices. In fact, I'm just going to kind of stick to our low-tech methods. I'm going to use elimination here and substitution here. So let's see what happens. So what do I want to eliminate? Do I want to eliminate x or y? Well, the smaller numbers seem to be in y instead of x, but they're both actually doable. I'm going to eliminate y though. So to eliminate y, we need the numbers to be the same. So I can multiply the top by 2, the bottom by 3. Now notice when you do that, you'll get 6y for both, and when you add them, you get 12y. So it doesn't eliminate, meaning we have to change the signs of one of the equations. So that's why I left space there. So I'm going to leave that as a -3 now. So now, in multiplying these, here's what we get now. Multiplying the top by 2 gives us 4x plus 6y equals 38. The bottom equation will give us -15x minus 6y now is equal to +6 because of the double negative. Adding straight down, notice the y's indeed eliminate just like we like them to. Here we get a -11x, I guess. And this is 44. Good. Why is that good? Because we can divide that by 11 and get a nice clean number, -4. As clean as it's going to get anyways here. Great. So now what? Now that we have one of the variables, we need to plug it into either of the two equations to find the last variable y. And just because the numbers are smaller in general here, or overall I should say, I'm going to plug it into the second equation. So the second equation, let me label that as 2, with x equals -4 plugged in, gives us 5 times -4 plus 2y is equal to -2. That's a -20 plus 2y is equal to -2. Add 20 to the other side. We get 2y is equal to 18. Divide by 2, and we get our answer for y, which is 9. So that means our total answer is the point x comma y, or -4 comma 9. Fantastic. Now, b, we could kind of do the same thing, but we have to make sure x and y are both on the same side. So we'd actually have to subtract 3x to that side. And it's actually really nice if you do that, because if you subtract 3x, you'll get -3x and 3x. They eliminate, so you'll get 2y is equal to 14, so y is 7. So it's actually pretty simple to do that. But you have to make sure that you have things ordered much like we had here first. But I'm not going to do that. I said it out loud kind of, but I'm not going to do it actually. Instead, I'm going to plug this into this, because y is already isolated. In the second equation, we can substitute it in for y to the first equation. So now our equation 1, with this in mind, becomes 3x plus y, but y is replaced with what it's equal to from the other equation, which is, 3x plus 1. Okay, so just to show that in parentheses, that's what y was replaced with, equals 13. Okay, good. Now what? Well, now, notice that if you kind of drop the parentheses because there's nothing to distribute, these combine to 6x, and if you subtract this 1 to the other side, that becomes 12. Dividing by 6 gives us x is equal to 2. Now remember, we got y is equal to 7, so let's see if that actually happens here. Notice since y is already isolated, plugging this into the second equation would be really ideal. So let's plug that into here. We get y is equal to 3 times 2 plus 1, which is 6 plus 1, which is indeed 7. Perfect. So we get y is equal to 7, so that means our ordered pair solution is the point x comma y, or in this specific case, 2 comma 7. Awesome. That was 6. Now let's move on to number 7. All right, so for number 7, we're asked to find the following given these two matrices, 2 by 2 matrices A and B. They're all a little different, of course. Here we're adding, here we're multiplying by a scalar -3 to A. Here we're subtracting 3 times A by 2 times B. And here we're multiplying B and A, but in this specific order. This was part D, by the way, my mistake. So now let's see if we can do this. I think we have enough space. Let's see. So A is 0, 5, 1, -2, plus B, which column-wise is 3, 4, -2, 1. And then adding matrices is just, adding component-wise. So the first entry to first entry, second entry to second entry in the first row, and then same for the second. So if we do that, 0 plus 3 is 3 for this entry. 1 plus -2 is -1 here. 5 plus 4 here is 9. And then negative 1 plus 2 is also negative 1 here. So this is our answer for part A. Perfect. So now for part B, all we're doing here is just multiplying the scalar negative 3 to this matrix. In other words, we're multiplying a number to a matrix. And how we do that is basically a scatter shot. This kind of, as I phrase in class, scales in. Basically, we're distributing it amongst all the terms, or entries anyways, in the matrix. So we get 0 times negative 3 is 0, 1 times negative 3 is negative 3, we get negative 15 and positive 6 here, and that's the answer for B. Great. Now, C is kind of like B and A combined actually, only there's subtraction now. But in fact, since we know scaling in a negative just kind of changes the signs of each of these, we can actually change this to addition instead of subtraction. So first off, I'm going to write this. It's going to be 3 times A, which we kind of just did, really. Well, kind of. There's no negative here, so it's a little different, but it's kind of the same. So A was 0, 5, 1, negative 2, minus 2 times B. B is 3, 4, negative 2, 1. Good. Awesome. So now I'll scale these in. So 3 scaled in is going to be 0, 3, 15, negative 6, just like that. And I'm going to make this positive, so I'm going to scale in negative 2 here. Negative 2 multiplied to these will change their signs, and multiply 2. So it's going to be negative 6, positive 4, negative 8, and negative 2. Adding component-wise gives us negative 6 for this entry, 7 here, 7 here, and a negative 8 here. Cool. Now, by far the most complicated part of this problem is definitely D, because how you multiply matrices is very particular, very specific. Let's take a look. So notice the order matters when multiplying two matrices. So B times A in that specific order, B first was 3, negative 2, 4, 1, and A second is 0, 1, 5, negative 2. Now remember, the way I like to explain it is that we're basically rotating the columns of the second one over to the rows of the first one. So first, if you rotate these entries over in this column, you can multiply these red numbers down and then add a cross. That gives you the new first column. So doing it that way gives us 0, minus 10, 0 times 4 is 0, 5 times 1 is 5, so plus 5. So if you combine these, and we'll do that for the second column as well, but if you combine these for the first, we get negative 10, 5 for our first column. Good. Now that we've finished multiplying the first column over, or rotating the first column over, we're done with that one, so now we're going to rotate the second column over as a row, multiply these red numbers down, and add across the results. So here, what do we get? Let's see. We get 3. Double negative is positive, so negative 2 to negative 2 is positive 4. So that's going to be 7 actually for the first entry in that column. So it's coming together quite nicely here. And finally here we get 1 times 4 is 4, and negative 2 times 1 is negative 2. Combining those two give us 2. So this is the answer of that multiplication. Let me move that a little bit, but yeah, that's fine. So good, so that finished off number 7, so now let's move on to number 8. All right, so number 8, there's only one part here finally, so it's hopefully less to do, but let's see. It's a graphing problem, so we want to solve the system of inequalities graphically. And in fact, the system of inequalities can really only be solved graphically because there's infinitely many solutions, so we'll basically just get a shaded region on the xy plane. So of course, what I'm going to do is I'm basically going to graph each one of these, and I'm just going to label it to make it a little easier on the eyes. Label these inequalities as inequalities 1, 2, 3, and 4. And really what I'm going to do is I'm going to graph the lines that correspond to these, meaning if you consider these being equal, we're going to graph those lines first. So x plus y equals 6. If you consider this, you can actually, well, cover each one to find the corresponding intercept. So for instance, if we cover x, we find out that the y-intercept is 6. If we cover y, we find that the x-intercept is actually also 6. So we end up getting this line for our first inequality. Now the only thing though is that remember that if it's or equal to, we actually draw a solid line. So in this case, we're good. But if it was not or equal to and strictly greater than or strictly less than, then it would be a dashed line. So we would have to kind of make a dash in that case. But in this case, it's solid because it's or equal to. Also, it says less than, so we would shade below the line. That may change depending on the sign of y, though, as we've seen before. But in this case, since y is positive, it is actually as is. And something to keep in mind that I find very helpful and always tell people to do is to pick a point, let's say 0, 0, plug it in and see if it works. And notice 0, 0 plugged in actually gives us something that works. It's less than 6. So that works in this case. So we shade that side of the line. Okay, good. But we'll shade after the fact because we have a few things to consider. Equation 2. So equation 2, much like equation 1, will be x plus 3y is equal to 9. And now notice here to solve for x by covering y, we get x is equal to 9. So let me make a little more room here for like a 9th number here. So that's 6, 7, 8, and then one more will give you 9. Perfect. So there we go. That's x equals 9. And what's the y-intercept? The y-intercept covering x. 3y is equal to 9 divided by 3 gives us that y is equal to 3, which is down here. So that's 9 and 3. These were 6. Good. So now connecting these two, we get this line, which I'll label 2. If you want to figure out where they intersect, that's actually not super difficult to do. In fact, if we're to scale, it looks like it's at 4, 2. It may not be accurate, but let's just check by plugging it in. So when x is 4 and y is 2, that actually works for the first one. So notice 4 and 2 add to 6. Again, assuming it's equals. And 4 and 2 into this one, does that work? That actually doesn't work because 4 times, here this is going to be 4 and then 2 times this is going to be 6. 4 plus 6 is not actually that. So it may be a little lower, just possibly somewhere else. But I'm not going to actually focus on finding that point. If you want to find it, you can just solve the system of equations. But again, I kind of digress. So now what we're going to do, now that we have these two lines, also notice that since it's less than and there's a positive in front of y, we shade below 2. So shading below 2 and below 1 is shading below these two like this. And now, x equals 0, the equality version of number 3, is actually just this line. Well, not really, actually. X equals 3 is this one, isn't it? X equals 0 is this one. Why is that the case? Well, remember, if it's a x equals line, it's a vertical line because it passes through the x-axis. So what I just showed, hopefully something nobody falls for. X equals a number is a vertical line, not a horizontal line. So the y-axis is actually the equation x equals 0. Similarly, the x-axis is the equation y equals 0. So this will actually correspond to equation 4. And, let me actually write this in black, I guess. Good. And by the way, when we're bigger than 0 for x and bigger than 0 for y, this basically just means we're in the first quadrant, which of course is why I only, gave us the first quadrant here in the xy plane. So now what? Well, now we're going to shade below these two lines and above the x-axis and to the right of the y-axis. So that shading will look like this. And just because I am the way I am, I will actually solve for this point, even though I said I wouldn't. It's going to be not too bad to solve for this point. So now I'm going to consider the system of equations with 1 and 2 equations, so equality. And notice if you multiply the bottom by -1, you get cancellation of x's actually. So we get x plus y equals 6 on top, negative x minus 3y is equal to negative 9 on the bottom. Add straight down, these cancel, we get negative 2y is equal to negative 3. And the y value, it's a little below 2 actually. It's a negative, actually it's positive, because divided by negative. It's 3/2, which is 1.5. So almost to scale. So 1.5 comma, what's the y value? I'm sorry, that's the y value. Whoops. So something comma 1.5. There we go. That sounds better. Now what's the x value? Okay, good. The x value, well, you can plug it into either of these. I'll plug it into this one. Plugging this into this one gives me what? It gives me x plus 1.5 is equal to 6. Subtract 1.5, we get 4.5. Perfect. So x is equal to 4.5. So our point is the point 4.5 comma 1.5. So it's a little bit to the right of 4 and a little bit below 2. So my scale was a little off, but it was kind of close actually. Great. But anyways, this is the answer for number 8. It's just this shaded region. And I'm plotting points just so I can be pretty accurate in what the what the region specifically is as far as what the corner points are. Speaking of which, that'll kind of correspond to a good transition anyways into the next problems 9 and 10, where we'll be taking a look at these corner points and solving I guess linear programming problems. So let's take a look at number 9 and 10 right now. All right, so like I was saying, number 9 here asks us to maximize, so it's a linear programming problem. This objective function, which is what we called it in that section, subject to these following constraints. So now really what we're going to be doing is graphing this region. Well, let me just say this. There are multiple ways we learned how to solve these linear programming problems. One was graphing. We also saw the simplex method, which was a non-graphical approach, kind of compares to the matrix approach opposed to graphing. But I think graphing is kind of the more intuitive way of doing it, and it's a little more simple to get a handle on. And it's quicker to write in the board too. So with that being said, let's do it this way. So what I'm going to do first is I'm going to graph this, and I'm going to notice here, these constraints here just tell me, like we saw previously with number 8, that we're in the first quadrant. So I'm only considering things in the first quadrant. Now, to graph these lines, well, let's see. 2x plus 3y is equal to 12. We'll have an x-intercept if you cover y. That says 2x is equal to 12. So divide by 2, you get x is 6. Okay, so this is definitely not going to be to scale, but let's see. And then similarly, if you cover x to find y, divide by 3, you get y is equal to 12 over 3, which is 4. So if this is 6, then 4 should be a little bit low. So let's just trying to make it somewhat to scale. Connecting these two gives us our line for the first one. Now, I'm not going to extend it because I know we have a feasible region which is going to be, well, finite in the sense we don't need the lines. But if you want to write the lines, you can. I'm just going to stop here and look at this segment only because we're only in the first quadrant. And I know that now. So now for the second equation, x plus 5y is equal to 10. Well, if you cover y, you get x is 10, which should be somewhere over here. And if you cover x to find y, you'll get y is equal to 10 over 5, which is 2. So that's like halfway between 4 and 0. So that's like that, and there's a line. Now, specifically, we need this corner point. And to find this corner point, we're going to solve the system involving these two equations, which are where these lines intersect. And we can multiply the bottom by 2, negative 2 actually, to cancel out x's. And what that gives us for the second equation is negative 2x minus 10y is equal to negative 20. The top stays the same, 2x plus 3y is equal to 12. Notice the x's cancel out. We'll get negative 7y is equal to negative 8. So that means y is equal to 8/7. Yikes. Not a very pleasant number. It's a fraction, of course, but still a number nonetheless. Let's see if we can find x given this. I'm going to use the original bottom equation because x doesn't have anything in front of it. So that'll be a little nicer, I think, when plugging this in. So when plugging 8 over 7 in for y, we get x is equal to, well, I guess x plus 5 times 8 over 7 is equal to 10. So that's x plus 40 over 7 is equal to 10. I know 10 is 10 over 1. I'm going to subtract 40 over 7 to that side. And of course, we need a common denominator. So if you multiply top and bottom by 7 to 10 over 1, you get 70 over 7. So x would then be 70 minus 40 is 30 over 7. So this point actually is the point 30 over 7, comma 8 over 7. Which makes sense because 30 over 7 will definitely be less than 6. 8 over 7 will definitely be a little bigger than 1, but still smaller than 2. So it makes sense, the placement makes sense. All right, so now what? Well, now we actually have the corner points. And by the way, since these are less than, well, we know from number 8 that it's actually going to be below those lines because, again, the number in front of y is positive. So specifically the feasible region will be this region here. So we want to figure out what these corner points are, which of course are the points 6, 0, 0, 0, 0, 2, and this one we just found, 30/7, 8/7. We're going to plug each of these into our objective function and see what the largest is because we're maximizing. So I'm going to erase all this, create a table, and let's do that right now. Right, so this is the table I was talking about. We have our x and y values corresponding to these corner points, 0, 0 being this corner, 6, 0 being this corner point, 0, 2 being this one up top, and then finally the one we just found, 30/7, 8/7. And now finally what we have to do is plug it into P, well, each of these into P. And notice 0, 0 will just give you 5 times 0 plus 3 times 0, so that's just 0. Okay. If you plug 6 and 0 in, you'll get 30 plus 0, that's 30. If you plug 0, 2 in, you'll get 0 plus 6, that's 6. And if you plug this one in, actually you'll get about, I got 24.9, I believe. Yeah, 24.9. And notice the maximum actually is 30, not this one. So even though we actually found it, it's found that corner point, it wasn't actually necessary, but we wouldn't know that until we actually tried it. So what I'll say is this, I'll say our maximum is P equals 30, and it occurs at the point 6, 0. And now we'll look at number 10. Number 10 is very similar, only now we'll be minimizing instead of maximizing. So let's take a look at number 10 right now. So 10 opposed to 9 now, a lot more going on as far as the constraints go, but that doesn't necessarily mean it's going to be harder. Well, it seems like there's more work, but let's take a look. So to find these lines, so let's take a look at 4x plus 7y is equal to 56. If you cover x to get the y-intercept, you'll get y is 56/7, which is 8. If you cover y to get x, let's see, 56/4, that's half of 56 is 28, and half of that is 14. There's going to be 14. I'm trying to be to scale, but it's going to be hard because we have a lot going on here. Let's take a look at the next one. X plus y is equal to 20. So if you cover x, you'll get y is 20, so that's going to be way up here. And similarly, if you cover y, you get x is equal to 20 as well. By the way, I should be actually graphing these like that. It's kind of interesting, but as it turns out, this lower line I don't think really matters, because since they're all greater than or equal to and positive in front of y, we're going to be shading above. So to be above this and above this is really just to be above the 2020 line, which is kind of interesting. In fact, I don't think that was intended, honestly, but that could technically happen. I mean, we're seeing it right here. So as it turns out, this is actually a stronger restriction than this one. There's no intersection, so it's actually less work to do, believe it or not. So that's fine. Good. So now what about 3x plus y? Let's see what happens here. So 3x plus y is equal to 36. To cover x to find y, we'll get y as 36, which is way up here. Yeah, so it's really hard to tell ahead of time what our scaling is going to look like. So this is obviously way off, but that's fine. And what about x? If you cover y, you'll get x is equal to 36 divided by 3, which is 12. It's going to be somewhere over here. So we get this guy. And if we're above all of these lines, because greater than or equal to, also, I didn't mention it, but notice this means we're in the first quadrant, so we're going to stay within these two lines here. So we actually get a feasible region that is unbounded. So it's not a finite region, it's an infinite region as it turns out. And there are only 3 corner points to this region, 0, 36, whatever that point is, and 20, 0. Now this point is where this line we just graphed and the 2020 line, which was x plus y equals 20, intersect. So we can solve this the system of equations to find where they intersect. And notice if we just subtract top minus bottom, this will actually eliminate y, but we have to subtract, so be careful. X minus 3x is negative 2x. 20 minus 36 is negative 16. Divided by negative 2 gives us x is equal to 8. if we plug that into, let's say, the top one, that, we get 8 plus y is equal to 20. So subtracting 8, that means y is equal to 12. So that means this point is really the point 8, 12. Which seems to add up with where it lies on the xy plane here. Good. So now what we need to do now is look at these corner points, plug them into C, much like we did with number 9, and then find out what the minimum value is opposed to maximum that we did in 9. So let me erase this and create that table right now. Right, so this is the table I ended up with. Notice the corner points here are 0, 36, 8, 12, which we just found, and then 20, 0. So now plugging them into C, let's see, 0 times 12 is 0, 36 times 36 is 1296. So that's what we're going to get for C here. 8 times 12 is 96. 12 times 36 is, I think we'll have to use a calculator there, but I'm getting like 5 something. And in total, we end up with 528. But I use my calculator here, so that's fine. When you plug in 20, 0, though, you'll get 12 times 20, which is 240 plus 0. And notice in this case, this is our minimum. This is the smallest of the C values. So what this implies is that our minimum value is C equals 240, and this occurs at the point 20, 0. Again, this problem is super similar to number 9, only minimum instead of maximum. I'm using the same exact procedure though. So now we're going to move on to number 11. All right, so now for number 11 is where the final exam review will start to go into the probability portion of the review. And basically we're given these things. We're given events A and B in the sample space S. A is 3, 5, 6, 7, 10. B is just the set of 2 and 6. And S are numbers 1 through 10, integers 1 through 10. And we're asked to find these things. Now, only 2 of which are probabilities, so we're actually asked something to do with set theory, basically, in problems part B and C. But let's first take a look at A, obviously. So remember that the probability of a set occurring is just the number of things in that set divided by the number of things in its sample space. So really what we have to do is count the number of things in A. There are 5 things. You can just count the amount of elements. You get 5. The sample space contains 10, and 5 over 10 reduces to 1/2. So the probability of set A is 1/2. Good. Now B asks for the number of things in the set A intersect B. So what I'm going to do first is I'm going to actually construct what A intersect B is. So it's the things that A and B share in common. So basically we'll look at the smaller one and see which one of these, if any, are in the other one. So the smaller one being B has less elements. 2 is not an A, but 6 is. So in fact, this is just the singleton 6, meaning the set of only one element. And in fact, from this, we can conclude the number of elements in that set is just the number 1. There's only one element. Good. Now, C says similar kind of, we still have an intersection, but it's A intersect B prime, which means the complement of B. Now, if you want to create a Venn diagram, you can kind of view it from that perspective, I guess. But really what we're doing is this. We're trying to look at all things that are in A, but also not in B. Because B complement means things outside of the set B. So outside of B, but still in the sample space S, of course, because that's our universal set, would be 1 through 10, excluding 2 and 6. So 1, 3, 4, 5, and then skip 6, so 7, 8, 9, 10. So that set I just mentioned, which is everything except for B, what they have in common with A, let's list it out. In fact, all I'm going to do really is write the following. I'm going to write things in A that are not in B. So 3 is not in B. 5 is not. We know 6 is, so I'm not going to write 6 because 6 is not in the intersection of A and B complement because it's in B. 7 is good and 10 is good. There we go. And now finally, part D asks the probability of B given A. So what's the probability of selecting an element in B given that that element is already in A? So clearly what we can see is that if it's already in A, we have 5 things to choose from, and the probability that one of those we select is in B, well, only one of these was in B to begin with, so clearly it's going to be 1 over 5. That intuitive way of thinking of it is probably the best way of thinking of it, but we actually have formulas for this. So we can actually write this as the probability of B intersect A, there we go, over the probability of the set that already occurred. This is B given A, so it's A has already occurred, given that A has occurred. And remember that the probability of A is just the number of things in A divided by the number of things in S. Similarly, the probability of B intersect A is the number of elements in B intersect A divided by the number of elements in S. So in reality, this formula actually simplifies a little bit to just, instead of probabilities, number of elements in those sets. Great. So notice this is exactly what I said when I spoke of this more logically. The number of things that are in B and A is just 1, divided by the number of things in A is 5. So it's 1 over 5. Now, if you wanted to write the probabilities as percentages, this would be 20% because it's 0.2 as a decimal. That would be 50% because it's 0.50 as a decimal. But I like fractions, so I'm going to leave it like that. That concludes 11, so now let's move on to number 12. So for 12, I'm not writing the whole question down in full sentence, but this is a counting problem. And it basically says that we're given that we have 15 shirts, 10 pants, and 4 pairs of shoes in a given wardrobe, and we're asked to find these following things. So part A says how many different outfits are possible. So in this case, well, for an outfit, it would consist of a shirt, pants, and shoes. So basically what we're going to, so let's say SH is shoes, and S is just shirts. So what we're going to do basically here is consider the slot method. And how I know this is applicable is because, well, we're picking one of each thing in a specific category. There's a category for shirts, category for pants, and a category for shoes. Now this should remind you of rank or order. Category is basically that. So for shirts, we have 15 things to choose from. For pants, we have 10. And for shoes, we have 4. So really this is, multiplying these is really our answer. Now, let's see, I know 15 times 4 is 60, so it's going to be 600 ways total. So 600 different combinations. I'll just box 600, I guess. Okay, good. So that wasn't too bad. In fact, there's a different way you can do this. Basically, you can say we're selecting one shirt to wear from 15 shirts. We're selecting one of our 10 pants and one of our 4 shoes. So basically, we're using combinations. We're using choose. So this is really 15C1, this is 10C1, and this is 4C1, meaning that we're selecting one of each of these amounts to choose from, basically. So that's a nice way to think of it, and that'll actually help in the rest of this problem. So B says, how many ways to select 3 shirts for donation? So from our 15 shirts, we're choosing 3 of them. There's no category there because it's already itself in a category of shirts. So we're not saying you have to pick a red shirt and a collared shirt or something like that. Just pick 3 of the 15. So that being said, here, there's no rank or order, or category, however you want to think of it. So that being said, we're going to use the combination C. So it's 15C3. And we can we calculate this by hand? I guess so. Let's see. You can use your calculator as well. But this is 15 factorial over 3 factorial over the difference, which is 12 factorial. And notice the top is, well, it's 15 times 14 times 13 all the way to 12 factorial. The 12 factorial cancels. 3 factorial is 3 times 2 times 1. And there's cancellation here, of course. 3 goes into 15 5 times. 2 goes into 14 7 times. And then we're left with 5 times 7 times 13. Let's see, 7 times 13 is 70, so it's 91. And that's going to be, times 5 is 405. So there are 405 different ways you can select 3 of your 15 shirts, which is a little mind-boggling, but it's just something to think about. And I'm going to move on then. All right, so now for C, how many ways to pack 6 shirts, 6 pants, and 2 pairs of shoes for this trip? So basically we're going to repeat B, but combined with A. Now there is order here, so basically we can use the slot method, but in each part of the slot method we'll have to choose not 1, but in this case 6 of them. So let's see. So for slots, so it's slot combined with that. So we have a slot for shirts, a slot for pants, and a slot for shoes. Now we're selecting 6 of the 15, so this is 15C6. We're selecting 6 of how many pants? 10 pants total. So it's 10C6. And then for shoes, we're picking 2 over 4, so that's 4 choose 2. And from here, I guess we can use our calculator because it's going to be a little much to do by hand. Should we do it by, I'll just try to do it by hand. So let's see. So 15C, let me write this as 15 times, let me see if there's a better way of doing this. It's going to be a little lengthy. That's fine. Let's just go through it. So we have 15 times 14 times 13 times 12, 11, 10, 9, 8, 7, and then I would write 6 factorial, but that would cancel with the 6 factorial in the bottom, and then their difference would be 9 factorial. So that's going to be 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So this is really what 15C6 is. 10C6 is, I think, not as crazy, but let's see. 10C6, I get 10 times 9 times 8 times 7 times 6 factorial, which cancels with the 6 factorial on the bottom. And then the difference factorial is 4 factorial, which is 4 times 3 times 2 times 1. And then 4 choose 2, that's pretty easy. That's 4 times 3 on top over 2 factorial, which is the difference between 4 and 2. So that's 2 times 1. Now, basically what I'm kind of unveiling here is a different way of computing combinations. Basically, you start with the big number, and you would basically increment it, or I guess go down. So you start a factorial until you have a total of the difference amount of terms. So until we have 9 terms. And then in the bottom, you just do a 9 factorial. Similarly here, we start with 10, and then create a factorial until we have a total of 4 terms, and then divide by 4 factorial. So that's nice. And we get cancellation. There's heavy cancellation here. In fact, all combinations will actually be integers. So there's going to be no denominators, there's no fractions. Which makes sense because what would it mean to have like 40.5 combinations in the end? Doesn't make any sense. So it should be an integer. So let's see if we can cancel these things. Of course, 9, 8, 7 just straight up cancel. 6 and 2 cancels 12. 5 and 4, well, 5 cancels 3 like this. 5 cancels 15 with 3 left out. There we go. That's what I meant to say. Oh, this 3 actually cancels that. So we could have just said 5 and 3 is 15. And then 4 is 2 times 2. So that goes into this 5 times, and then into this 14 7 times. So that 2 times 2, it kind of split and got those 2. So really what this is 7 times 13 times 11 times 5. Now 7 times 13 times 5, I did up here, that was 405. And 405 times 13, I'll have to use my calculator there. So I'll do that. But let's see cancellation here. 4 times 2 is 8. 3 goes into 9 3 times. So this one's actually pretty nice. That's just 10 times 3 times 70 times 7, which is 70 times 3 is what I meant to say. So this is 210 for sure. And this is really just 12 over 2 for this one. You can kind of see it by doing this. 12 divided by 2 is what I meant to say. So that's going to be 2 times 3, which is 6. And then this, like I said, I'll just write it out. So it's, well, again, we know 7 times 13 times 5 is 405, and then we have that 13 here, that 11 here, sorry. So this is 11 times 405. So now let's multiply through with our calculator. It's going to be a pretty large number, so there's a total, well, a large amount of combinations you can actually choose from here. So let's take a look at what the calculator gives us for this multiplication. Yeah, we indeed got a rather large number here, 5,613,300 different ways to pack for this trip. So yeah, that's again something you can think about as far as why that happens. But again, it just has to do with the total amount of different ways you can do this as far as selecting. So if you pick one shirt, then you have 6 and 2, so there's 12 for that one shirt. But but then you can kind of play the same game with each of those. So it really becomes quite a large number. It grows pretty rapidly. So anyways, with that said, let's move on to number 13 now. Alright, so for number 13, we're being asked that in drawing one card from a standard 52 card deck, what is the probability that the following happen? Now 13 really is a combination of what we saw from number 11 and number 12 because it is probability question but mixed with some counting. So we have to use some techniques from counting to figure out what the number of things are in a certain set, basically. So here, if you recall how a standard 52 card deck is constructed, there are lists. If you look online, you can just Google search an image. The best way of doing this is Google image search, and you'll get actually a grid with different suits. I guess it would be suits here. So it'd be suits like spades, hearts, diamonds, clubs, and then ranks. So A, 2, 3, all the way to J, Q, and K. And once you study that for a little bit, you'll kind of see the structure. So there are 4 aces because there's 4 suits. 1 ace for each suit. So the probability of drawing an ace, so let me write this as probability of A, are the number of aces divided by the number of things in the sample space. Now the sample space here is how many ways we can draw 1 of 52 cards. So notice to draw 1 of 52 cards, there's 52 cards to choose from. So really this is 52C1, kind of like we saw in problem number 12, in the previous problem. Now how many things are in A? Well, how many choices do we have to choose from as far as to pick an ace? So we have 52 cards to choose from, but then only 4 of those are ace. That reduces to 1 over 13. So that's the probability for part A. That was not too bad. Now what about B? So B is a little different. Here we're asked to find the probability that it's an ace or it's a spades. Now if we recall the formula we actually saw for union, probability of union of 2 sets, this is actually equal to the probability of one set plus the probability of the other set minus what? Minus the probability of their intersection. This is a pretty important concept, and in fact, if you take a look at those grids I was talking about, if you do Google search on your own, you'll actually be able to count the number of things that are either an ace or a spade, and you'll see that it's not just adding the amount of spades and the amount of aces because of the ace of spades. If you count the amount of aces, there are 4. If you count the amount of the spades, there's 13 spades because there's 13 ranks. And so that's A through K. And 4 plus 13 is 17, but as it turns out, there's only 16 in that list because we would be counting the ace of spades twice. So notice if you count the aces, that's 4. If you count the spades, you're also counting the ace of spades again. So to basically deduct the double counting, we subtract what they have in common. So this really is the ace of spades. So let's take a look to see if we can do this. So the probability of being an ace, we know that. We actually just did that already. And I'll leave it as over 52, just so the calculation will be a little easier. So 4 out of 52 is what we got before reducing. Probability of spades, So probability is a spade, there are 13 spades, so this is going to be 13 over 52. And the minus 1 out of 52 for it being an ace. And as I said already, 4 plus 13 is 17, but minus 1 is our 16. And 16 over 52 reduces by dividing by 4, much like we saw in part A. And this is 4 over 13 now, though. Great. Good. All right, so now for C, a little different. What is the probability that it's an ace given that it's a spade? So if we're given that it's a spade, remember how conditional probabilities work that we saw in number 11. There are 13 spades, so if you drew a card and you know that it's a spade, well, there's only one ace that's a spade, so chances are this is going to be 1 out of 13. But just so we kind of abide by the probability formulas, let's see if that actually makes sense. So we want to find the probability that it's an ace given that it's a spade. And the formula we saw for conditional probabilities was the probability of A intersect spade. So this is the probability of it being an ace of spades, divided by the probability that it's, well, in the given set, spades. And we actually know that this formula is equivalent to replacing the p's with n's. So looking at the number of elements in those sets instead. And that's actually easier to calculate. There's only one ace of spades in the entire deck, and there are 13 spades themselves. So it is indeed 1/13 like I suggested when I went about it kind of more logically. So that concludes 13, and now we'll move on to number 14 finally. Alright, so this problem number 14 is definitely the hardest problem in the whole review because it's it's an application problem, so it's very wordy, and we have to kind of build things up accordingly. So let's just see if we can follow. So it says a jar contains 7 green, 13 blue, and 5 red marbles. A game is played where you pick 2 from a jar at random, so 2 marbles from the jar at random without looking basically. If you draw 2 of the same color, you are rewarded $8 for green, $5 for blue, and $10 for 2 reds. If you draw 2 of different colors, there is no prize. So if you draw a red and a blue, then there's no prize awarded to you. The fee to play is $2, so there's an entrance fee here, okay? What is the expected value and is the game fair? And then finally, how should the fee be changed to make it fair if it's not fair? So first off, we're finding expected value. Now, in an expected value problem, you always want to have what? You always want to have some probability distribution. So you have a random variable x, and then you have, probability of that random variable x. So now in this case, there's going to be essentially 4 different categories here, or 4 different values of x. Basically, if you, depending on what you pull off. So what you can do, if you kind of think about actually running through this game, either you can get 2 green, 2 blue, 2 red, or 2 of different colors. Those are the total possible outcomes. There are 4 outcomes. So this bottom row will represent the sum of these. Now remember that in a probability distribution, all the probabilities should add to 1. Keep that in mind. And x here will be our value. So it's how much we'll win or lose depending. So we're already down $2 right away in the game. So let me just label this as a G for green, B for blue, and R for red, and then N for none. So we get 2 different colors. So in this case for green, we win $8, but we lose 2 as soon as we enter the game. So in total, we're a net $6. Similarly for blue, the price for blue is 5, but then minus the entrance fee of 2. That's a total of $3 net. And then for red, it's $10 minus 2, so that's going to be 8. Okay, good. Sorry, 10 minus 2 is 8. There we go. And none, so if we get 2 of the same color, we have a prize of 0 and minus our entrance fee, meaning we're down $2. Great. All right, so now we need to find the probabilities of these things. What's the probability of drawing 2 greens? So let's think about this for a second. So the probability of drawing 2 greens is, we basically have to use a slot method here, but for probabilities. In fact, this is essentially a conditional probability problem because we want to know the probability of drawing green, given that we already drew green, and multiply that to the probability of drawing green. So notice how many marbles are in the jar total. Well, there's 7 plus 13, which is 20 plus 5, so it's 25. Now we want to draw green, so there's going to be 7 out of those 25 will be green. Multiplied by, for our second draw, if we want to draw 2 green, then there will be 1 less green, so 6 now in the jar, out of 24 because we already drew 1 without replacement. So we draw 1, then we draw another one basically. So that's kind of what's going on here. Now this reduces, I don't know if we want to reduce this or not. Maybe we should just keep it in a common denominator. Of course, we're going to multiply these to find the expected value afterward the fact. For right now, I will reduce it. So 6 goes into 24 4 times. So this is 7 over 100. So that's the probability for this one. Good. Now what about probability of drawing 2 blue? So same idea. So out of 25 marbles, how many are blue? 13 are blue. And then for our second draw, we'll have 12 blue out of the 24. Now in this case, 12 goes into 24, twice. So this would be 13 over 50. But I like having the common denominator of 100. I think that's going to play out quite nicely throughout here. But let's see. So let's try to do that. So I'm going to say this is, so I want this to be 4. So I'm going to divide top and bottom by 6. So it's going to be 2 over 4, so it's 26 over 100. I think this sounds okay. Hopefully we get a denominator of 100 for all of these. The next one, let's see. So the probability of drawing 2 reds. So probability of drawing 2 reds is, how many reds are there in there's 5 reds. So 5 out of 25 multiplied to 4 out of 6. 4 out of 24. There we go. So basically we reduce each one. That's kind of what's been going on here. And yeah, we can, well, unfortunately the denominator isn't 100 here. But it's, I mean, well, let's see. So this reduces to 1 over 5, this reduces to 1 over 6. So in total this is 1 over 30, which is still not too bad. In fact, there's a common denominator here, and the common denominator is 300. So if you multiply each of these top and bottom by whatever you need to make them 300 in the denominator, you'll see that the top one, so I'll write in this piece over here, will be 21 over 300. The one below that will be 26 times 3. Let's see, 26 plus 26 is 52, plus another 26 is 78, so it's 78 over 300. And then finally, top and bottom by 10, here will give you 10 over 300. Great. Now the reason why I'm doing this is because I want to figure out what the probability of drawing none of the same color is. And it's basically just 1 minus these added. And since we have them as a common denominator now, we can clearly see that they add to, well, let's see. These two add to 31. 31 plus 78 is 109. I think that makes sense. Good. So this is going to be 1 minus, so the next thing here is going to be 1 minus these added, which is a 109 over 300. And I'm going to erase this and actually write out what the answer is, because of course 1 is 300 over 300. So 300 minus 109 is, what's that, 181? 191, it's 191. So in total, this probability is 191 over 300. And of course, if you want to write this as decimals and approximate, you certainly can, but I'm just trying to stick to accuracy here. And now multiplying these straight across, I'm going to try to keep that denominator of 300, but it actually seems like 150 is okay. So you know what, let me do that. Let's just multiply across and reduce as needed. So notice that 6 goes into 100 2 times, so you can cancel 2. So if you cross cancel 2 here, you get 3 left over. So 3 times 7 is 21 over 50 now. So really, if you multiply across, you get 42 over 100, but that reduces to this. Similarly, here there's no reduction actually. Well, kind of. Because remember that 26 is 13 over 15. 13 times 39 is 13 times 3 is 39. Keep kind of talking over myself, sorry about that. This you can reduce by dividing by 2, and you get 4 over 15. And then here you get negative 191 over 150, because of course 2 goes into 300, 150 times. And now add these results, and that'll be our expected value. Now, of course, we can use our calculator, but again, I'm going to try to keep this as exact and kind of do it by hand just to show you. So if you multiply top and bottom by 3 for the ones with 50, and by 10 for the one with 15 in the denominator, we end up with a common denominator of 150. So let me see if I can write that result here. I don't think it's actually too bad. So 21 times 3 is going to be 63, plus 3 times 39, well, let's see, 3 times 30 is 90, 3 times 9 is 27, 90 plus 27 is 117, good, plus 40, minus, because this is negative 191, and then all over 150. Nice. Let's see if we can do this. Oh, this is nice. So look, these two actually combine to let's say it's 170, 180. They add to 180. And 180 plus 40 is 220. So 220 minus 191 is going to be 29. So this is actually just 29 over 150. Now at this point, I'm going to definitely use my calculator and figure out what this is approximately, and that's going to be our expected value. Right, so after approximating in the calculator, I got 0.1933. And of course, these values here represent dollars. So what we can say is the expected value is 19 cents. And that's my answer here for the first part of this question. Is the game fair? The game is definitely not fair, because remember what fair means is that your expected value is 0. And then finally, how should the fee be changed to make it fair if it's not fair? So we know it's not fair. So how do we change the fee? Basically, the fee would have to be reduced by this amount. And I can leave it to you to kind of figure the details of that. But basically what you can do is you can change this 2 here to F for fee. We've done this in an actual review problem for exam 4 review. Multiply it to the same probabilities. You'll get an equation for F. You want it to be fair, so you want the expected value to be 0 here. So that didn't come out actually, but you want this to be 0. There we go. And you can actually make that work. So multiplying a minus f to this number, 5 minus f to this number, and so on, you'll actually see that we'll get something very, very similar. And basically what happens is that f would have to be, well, 2 less than this to bring this down to 0, basically. So again, I'm not going to go through the details of that, but you can try that on your own. And I think that was enough to say about the final exam review. I really hope everyone enjoyed it. I know I went a little fast in some places, maybe slower in others, but you know, that's just the way I do things, I guess. And I hope you enjoyed the class. That's kind of like, I guess, the last video really for the entire class, so it's kind of exciting. I wish everyone luck for the final exam, and see you around. Thanks for watching.